Hi, my name is Darshan Patel, and this is my lab video for Physics 1 Lab 5. And the topic of this lab is the rope swing. So, a brief introduction is, why a rope swing? Well, it's a system that naturally hits several core topics from this course. So first, there is the conservation of energy, which potential energy at the top is being converted to kinetic energy at the bottom. Second, there's circular motion and centripetal force. The rope has to supply a net inward force to keep the swinger on a curved path. And third, when you let go, it becomes a projectile launch problem. And we can actually predict exactly where you land based on when you release. This is a mini capstone of Intro to Physics. So here's how I define the system. The swinger, who is about 70 kilograms, holds a rope that's 4.5 meters long, anchored to a tree branch. They start at rest at an angle of 45 degrees from vertical. Using the geometry, that gives us an initial height of 1.32 meters at the bottom of the swing. The surroundings include Earth's gravity at 9.8 meters per second squared. I'm going to neglect air drag as a first order approximation, and this will be justified later in the error section. The anchor point is treated as rigid. These are our starting conditions, and everything else follows from here. So now for the physics. I used three models. The first one was the conservation of energy. At the bottom of the swing, all the initial potential energy has converted to kinetic energy. Setting those equal and solving for velocity gives us V equals the square root of 2gh naught. Plugging in the 1.32 meters, I predict a bottom speed of about 4.98 meters per second. Second, the centripetal and tension forces. At the bottom, the rope tension minus gravity equals the centripetal force. Solving for tension gives T equals m minus the quantity g plus v squared over L. That comes out to roughly 1,548 newtons, which is about 2.2 times the person's weight. That's important for safety. Third, projectile launch. Once you let go, you're in a free fall. I can use standard kinematic equations to find the horizontal range as a function of what angle you release at. The model predicts maximum range at a release angle of about 35 degrees from vertical. So to test these predictions, I filmed a real rope swing at about 60 frames per second, placed at a reference marker of known length for the frame, and used tracker software to extract the X and Y position of the swinger on every frame. And these are the results. I measured a bottom speed of 4.94 meters per second. The model predicted 4.98. A period of 4.28 seconds predicted 4.26, and a launch range of 5.1 meters and predicted 5.3. As you can see on the bar chart, measured and predicted values are very close across the board. All errors are under 4%, which I'm really happy about given how simple the model is. So now here's the GlowScript model. So alongside the real-world experiment, I built a GlowScript VPython simulation. The code initializes a pendulum with our measured parameters and runs a physics loop, updating position every 0.01 seconds using Newton's second law for the restoring force. This simulation plots kinetic energy, potential energy, and total mechanical energy in real time, confirming that they are conserved. It also lets you interactively change the rope length, mass, and release angle, which I use to explore the what-if questions when the swinger releases. The code switches to a projectile motion and calculates the landing range. So, the what-if questions and what does it mean? So first, what if the rope were twice as long? The period would increase by a factor of the square root of 2, so from 4.26 to about 6 seconds. But the bottom speed stays the same since we're releasing from the same angle, and this is confirmed by the GlowScript code. What if mass is doubled? Interestingly, mass cancels the energy equation. Speed at the bottom is identical, but tension doubles, which is a safety concern. So what if we released at about 60 degrees instead of 45? The launch speed jumps to about 6.14 meters per second. The range increases by about 50%. And for what this means is the fact that our model works so well with such simple assumptions tells us that the energy conservation is robust, even with approximations, and that the tension calculation has a real practical takeaway, which is always making sure that the rope is rated for more than twice your body weight. And to wrap it all up, so for our sources of error, my biggest one was the camera angle, which filming slightly off perpendicular produces 2 to 3% of error, and air drag was also neglected, but is generally small with these speeds, and rope elasticity could also absorb a small amount of energy. So the rope swing investigation successfully connected conservation of energy, circular motion, projectile physics, and computational modeling all in one system. The model predicts matched real data within 4%, and the GlowScript simulation let me go beyond what I can measure in real life. So thanks for watching. This is the end of the lab video.